Okay. The first topic we'll be covering for this course on current topics in amplification is binaural and bilateral considerations in hearing aid fitting. This chapter that you'll be assigned to read is out of the Dillon book that we've used in previous classes. I hope you were able to hang on to that from previous semesters, but if you haven't, I've got the scanned copy of the chapter uploaded onto Blackboard. I wanted to cover these sections individually, so I'll have a separate lectures on different sections of this chapter to kind of break it out so you can watch different parts individually, but try to stick in order if you can. The first section I wanted to cover was binaural effects and localization. So in particular for this one we're going to be covering just some of the normal processes on how we localize sound for normal hearing individuals in the beginning, and then I'll also talk about how persons with hearing loss are affected as well. So some of this stuff in the beginning should definitely be a rehash from your psychoacoustics course from last year. 5 different ways we can kind of categorize sound localization. They're not really fully independent of one another, but at least 5 different ways that they are talked about or thought about in terms of psychoacoustics and hearing science. We've got horizontal localization, so being able to figure out where things are coming from in the horizontal plane, right, left, front, back. We've got vertical localization, so figuring out where things are coming from, say, above you. We've got front-to-back localization or front-to-back differentiation, just like it sounds, telling the difference between a sound coming from in front versus behind you. Externalization is kind of a little bit of a different one, just the general idea that we can tell that sound is coming from somewhere outside of our own head, outside of our own body. And then distance perception would be being able to tell how far away a sound is or an object is from you. So the first we'll talk about, and probably the one that we think the most about when we talk about sound localization, especially as it pertains to hearing loss, is horizontal localization, or in particular left-right localization. And this is the classic localization that we talk about with interaural differences, so differences between the ears in arrival times and in intensities. So in the diagram below, you can see that there is a speaker at, say, roughly 45 degrees azimuth, and that speaker is going to arrive sooner at the near ear, and it's also going to be a little bit louder at the near ear. Well, the reason it's going to be a little bit louder is because the distance is shorter between the source and the near ear in comparison to the source versus the far ear. The reason it's going to arrive sooner in terms of time would be, again, because it's located closer to the source. So it's going to arrive there sooner because the speed of sound isn't going to change. Speed of sound is constant, so it's going to arrive sooner at a location that's closer. So it's taking advantage of these differences in terms of central processing and the say the midbrain on up. We're taking advantage of hearing the differences between comparing what we're hearing at the right ear versus the left ear, and our brain is able to process that, and we are able to determine what the nature of those differences are quite subconsciously in order to attribute location in space. Here's a diagram to separate out interaural time differences versus interaural level differences. As you can see on the left with interaural time differences, we're looking at delta t, so differences in timing or really phase differences between the ear. It's kind of how the masking level difference test works as well. And then on the right side we've got interaural level differences, so delta I, differences in intensity between the two ears. And of course, if we had a sound source that was around 0 degrees azimuth, we would expect that there really would be no differences in interaural timing or interaural level. So if we want to think about how interaural timing differences, for starters, how interaural timing differences are affected by angle of incidence or the horizontal azimuth, We can see from this graph over here that as the horizontal azimuth increases from 0 to 90 degrees, the interaural timing differences increase up to a maximum around 0.7 milliseconds for low frequency sounds. You can see 90 degrees here, or negative 90 here, similar to 270. And so this is primarily for lower frequency sounds. Higher frequency sounds, there is still an interaural time difference effect, but it's really not quite as useful. It's definitely going to decrease as frequency increases in terms of the overall timing. It'll be about 2/3 of what it is for lower frequencies, and so we find that interaural timing differences are at best around 700 or 800 hertz, so really 800 hertz and below, but they're still pretty darn good for 1500 hertz and below. Okay, so let's move on to interaural level differences. So the main reason why we have interaural level differences, say when we have sound coming, for example, from 90 degrees azimuth, in addition to the distance factor, where we may have the sound source being closer to the ear, the other factor is going to be head diffraction. So the head is going to act to attenuate sound for the far ear, and it's also going to act to boost the sound toward the near ear, or the near side. This head diffraction typically is going to be maximum for higher frequencies, so those frequencies that have a wavelength that are much smaller than the diameter of the head, and it's usually going to be frequencies that are above about 1500 hertz. Actually, our horizontal localization ability is its worst right at 1500 hertz, probably because that's where interaural timing differences and interaural level differences are both the least salient, whereas our localization, horizontal localization abilities are really, really pretty good, around 800 hertz. So if we look at what the interaural level differences kind of look like as we go from, say, around 30 degrees to 90 degrees, as we change that horizontal azimuth, we can see that the level differences, we do have level differences here for low frequencies, but they really become much larger above 1500 hertz. Kind of a simplified figure over here would be where we've got a sound at 90 degrees azimuth relative to the head of the speaker, the head of the listener. We've got the speaker located at 90 degrees azimuth, so we can see the darker area of this figure represents more intense sound. This kind of less densely populated, more sparsely filled in area is weaker sound. Here, right below that, again, the sound coming, this is the low frequency sounds that are coming from this sound source over here, and the reason that these sound waves look about the exact same on the opposite side of the head is because the head diffraction isn't going to have a big negative impact on the intensity of those low frequency sounds. It'll mainly affect the high frequency sounds right here in panel C, in figure C, and when we have that head diffraction causing attenuation at the far ear, we call that a head shadow. Moving on from horizontal localization to front-back differentiation, or front-to-back discrimination. This psychoacoustic ability is primarily dependent on the very high frequency sounds, so 6K and above, in order to differentiate between the frontal location and back location. So it's really these spectral differences that we're looking at that are created by the shape of the kind of the folds of the pinna. So because of these foldings of the pinna, it creates these reflections which cause these resonances and anti-resonances, these spectral dips and peaks, and these kind of the shaping of these sounds from 6 to 16,000 hertz. It's able to kind of let us know if things are coming from the front or the back. So if they're coming from the front, these sounds are going to be boosted, and if a sound is coming from the back, these sounds will be attenuated. It's important to also mention another aspect of front-to-back differentiation. Whenever we have sound coming from this particular area here called the cone of confusion. If we have two sounds, if we take sound A and it's intersecting the perimeter, any one point on the perimeter of the cone of confusion, then we take sound B and that intersects another point on the cone of confusion along the perimeter, then those two sounds are going to be very easily confusable for a normal hearing listener. And the reason is because we're not really going to be able to take advantage of interaural time and level differences. So to give you an idea here, even though we have sound source 1 on the upper right and sound source 2 on the lower right, even though source 1 is kind of coming from the front, it's about 30 degrees azimuth, and sound source 2 is kind of coming from the back, it's about say 120 degrees azimuth. What we've got going on is with both of those sounds, we have it's softer on the left ear, and the timing is going to be there's a longer latency on that left ear. And so regardless if we're talking about the sound coming from source 1 or source 2, our brain is going to process it in a very, very similar way. So that's hopefully that kind of helps you better understand the idea behind that cone of confusion, where we're going to have certain areas to the right and left of us where we're not going to be able to easily discriminate front and versus back. Moving on to vertical localization, we're really taking advantage of a lot of the same things in terms of spectral shaping, or that Pinna effect with vertical localization, because when sounds are say changing in the elevation, again it's going to be the infolds of the Pinna that are going to be creating constructive and destructive interference, which result in these spectral peaks and dips, and the exact frequencies at which those peaks and dips occur at are going to vary as elevation changes. And so this isn't quite as dependent on quite as high frequency sounds as front to back discrimination is. This is about 4K and higher. And we also have externalization. Externalization where I have the sense that the sound is coming from somewhere other than inside our own head. So with externalization, the main reason we externalize sound is because of filtering effects of our own body. In particular, the spectral filtering effects of our head, our pinna, our torso, in the combined filtering effects of the head, pinna, and torso result in an individual's head-related transfer function. So the head-related transfer function just describes the transform that's required to convert SPL in the free field to SPL in the ear canal. In some ways, if you're trying to relate this back to something else we've talked about in hearing aids, a real ear unaided gain is kind of like a head-related transfer function. Real ear unaided gain is kind of the conversion from SPL in a diffuse field to SPL in the ear canal. So the head-related transfer function is has a different reference points a free field, and this is more of a kind of a basic psychoacoustic measure as opposed to a clinical measure. But it does come up when we talk about certain hearing aid technologies, like some hearing aid manufacturers have things called, I think Siemens has one called True Ear, and I think maybe Unitron just calls it the Pinna effect. But a lot of manufacturers have something like this, where they're trying to take into account an individual, or the average head-related transfer function it's kind of getting distorted when we move put BTE hearing aids on when mics are placed behind the ear. So to kind of give you an idea of how this also might be useful, how this head-related transfer function might be really useful for another population, if we're talking about somebody who say is blind, or somebody who has single-sided deafness, they may be relying on the changes in the head-related transfer function as they move their head. So in this particular figure in front on the left side, you can see that the head-related transfer function is changing as the elevation of the head goes up, or as the sound source changes. And so a person could move their head, and they could learn how these patterns create this perceptual learning where they learn how these patterns are changing with head movements, not really consciously that they're doing this, but they're doing it kind of naturally over time, and they can use this to help kind of get a better understanding of the world around them for someone who's blind, or just get some small degree of horizontal localization abilities or vertical localization abilities with single-sided deafness. So now let's move on to talking about the effects of hearing loss on localization. So with hearing loss, it absolutely is going to impact sound localization in many different ways. The first thing to mention would be when you have somebody to come in your clinic, they're usually not coming in saying, oh, I've got sound localization abilities. They're saying, oh, I can't hear well in noise. I can hear, but I can't understand in a background of noise when there's a lot of people talking in a restaurant or something like that. So, but we do know that these people have localization deficits when they're specifically asked. They may be asked in an informal manner, or they might be asked in terms of a specific questionnaire like the SSQ, which might address sound localization abilities and deficits. But there's been an increased interest in recent years for hearing researchers to look at the importance of sound localization abilities for hearing aid users or persons with sensorineural hearing impairment. Because it likely is a contributing factor to some of these difficulties in noise, above and beyond just needing a greater SNR to hear in noise. It's going to, one thing would be if you think about a conversation where there's more than one person that a hearing impaired person is talking to. Say they're talking to, they're within a group of 4 people, themselves and 3 other talkers. As the conversation moves along, very likely there'll be a transition from one talker to another, and that hearing impaired listener has to realize when that shift occurs. And a normal hearing person is going to use typical sound localization abilities. Even in noise, we can do that. It's not as good as if it's in quiet, but we can still do that. But the hearing impaired listener, their localization abilities in noise are going to be much worse. And so if it takes them longer to localize the location of the new talker, then they've already missed some of the conversation. They're going to have to catch back up, and very likely it's going to be hard to do, especially with a very poor SNR in that environment. Another area that's relevant to hearing loss and localization would be a new hearing aid user. Well, a new hearing aid user's sound localization ability is very likely to get worse initially because their brain hasn't really learned the way to process these new cues binaurally. It could get worse for a variety of reasons. It could be related to the hearing aid processing, but it could also just simply be related to the change in the way the typical levels that the sound is the stimulation levels that the brain is receiving. Hearing loss is definitely also going to contribute to front-to-back confusions. Remember, front-to-back confusions are going to be for frequencies really between 6 and 16,000 hertz. So this is a frequency region where hearing impaired listeners do very poorly to begin with, because the nature of hearing loss, sensorineural hearing loss, is often that it is in the high frequencies. So hearing aids probably aren't going to help that all that much. However, an interesting technology would be, frequency lowering. Can frequency lowering have a benefit on front-to-back localization or discrimination? Other things to consider that I've seen researchers talk about have been binaural processing in hearing aids. Can that improve or decrease front-to-back localization errors? And I think it's been shown that it can. Horizontal localization is usually going to be the best preserved of any of these localization abilities, and the reason is because it's the least dependent on high frequency hearing. Horizontal localization abilities is going to be more dependent on interaural timing cues than it is interaural level cues. And if we think about the sounds that are, or at least communication, if we think about communication, that's the most important to us in everyday life. It's usually going to be a broadband signal, and those broadband signals are going to have greater intensity at low frequencies to begin with. So it's usually not until someone has a pretty substantial low frequency hearing loss, so when their thresholds are exceeding 50 dBHL, that they're really going to be impacted in terms of horizontal localization. That's not to say that that someone with sensorineural hearing loss can can localize sound as good as somebody with normal hearing. That's not what I'm saying, but I am saying that it's going to be the least effective of all of the, compared to, say, vertical localization, front-to-back discrimination, etc. So other impacts, other types of hearing loss to consider would be conductive hearing loss. Well, conductive hearing loss, maybe come as a surprise, but it'll have a greater impact, or it can have a greater impact on sound localization compared to sensory neural hearing loss. And the reason would be, especially as conductive losses get greater, that's going to mean that there's a greater proportion of the signal being transmitted to the cochlea via the bone conduction pathway. And because the bone conduction pathway has negligible interaural attenuation, they're not going to get to take advantage of those interaural timing cues. We're going to have, and it's also something else on the flip side of that. That's kind of a downer, that conductive hearing loss can cause such great impacts, negative impacts on sound localization and the horizontal sound localization. But another thing would be asymmetric sensory neural hearing loss. In a population you would think that would have very poor localization abilities, they can actually do okay because the brain has adapted to the different sensation levels between the two ears. But the key thing is, if in the poor ear, if the signal's not audible, well, they're not going to be able to localize it in terms of the horizontal plane. So it has to be audible in both ears. You typically want like a 10 dB sensation level in each ear, or at a given frequency. But as long as it's audible, you can probably do okay with asymmetric sensory neural hearing loss. An interesting thing to consider would be someone who has, say, binaural hearing aids, but they're aided in one ear. Maybe there's very likely, I suspect, that it would decrease sound localization abilities initially, but then maybe you would see an improvement over time. Okay, some other effects of hearing loss on localization. Well, regardless of whether you have hearing aids or not, vertical localization is going to be impaired because we're talking about frequencies that are really above 4,000 hertz. Maybe you could get a little bit of benefit, especially if we're talking about a fairly mild high-frequency hearing loss with some of these newer hearing aids that have extended bandwidth out to, 8K or 10K. Maybe. Another thing to mention, I haven't really talked about distance perception at all, and it isn't really talked about that much in terms of hearing science and audiology. I think it's probably more psychologists who study this area. Hearing loss does have an effect on our ability to perceive or judge distance in terms of compared to the sound source, but hearing aids really don't cause any further decline in that area. And that's all I've got for this section on binaural and bilateral considerations in hearing aid fitting. That was binaural effects and localization. I will have another segment of this chapter posted in the very near future.